So up until this point, we have discussed why certain substances exist as solids, liquids, versus gases with respect to their intermolecular forces. And now we're actually going to look at the heat that is involved in changing those states of matter. So as a quick review, some of these terms you're probably familiar with already. When a liquid becomes a gas, we call that vaporization. Now you might have heard of the term boiling. You also might have heard of the term evaporating. Vaporization is simply an umbrella term that refers to both boiling and evaporating. Boiling occurs at a substance's boiling point. Evaporating occurs simply when a liquid becomes a gas. The opposite of vaporization is going from a gas to a liquid, and that is called condensation. Okay? That's why whenever you bring a soda can out of a fridge, it becomes wet. That's because the water particles that are in the air will actually slow down enough so that they can become a liquid. And the reason why they slow down is because the can is cold, causing them to become a liquid. So it's not that you have a leak in your can, it's simply condensation that's forming from the water molecules that are in the air. Okay? Now, if a liquid goes from a liquid and it transforms into a solid, we call that freezing. The opposite of that, a solid to a liquid, is called melting. Now, the last two are potentially terms you've never heard of before. A solid can actually go directly from being a solid to a gas. We call that sublimation. That's what happens when you have dry ice. And deposition is when that gas becomes a solid. We're not going to be studying these two terms in detail. We're not going to be looking at the energy that's involved in those processes, but I did want to make you aware that those processes do exist. Now, what you see right here, this is what we call a heating curve. So I'm going to walk you through what's happening in this heating curve. At the base of this heating curve, my substance exists as a solid. Then as you move up the curve right here, what's happening is that solid is increasing in temperature until it reaches this point right here. And in this example, we're specifically talking about water. Okay? At this point right here, you will still have a solid, but at this plateau, at this flat area right here, it's going to transform from a solid into a liquid through the process called melting. Now note that this melting occurs at 0 degrees Celsius. So that is the melting point of water. Substances have different melting points, but that of water is 0 degrees Celsius. Okay? So as I'm going through this, as I'm moving across, the reason why my solid increases in temperature and the reason why my solid becomes a liquid is because I'm putting energy into it. Okay? If I keep putting energy into the substance, then that liquid will start to increase in temperature, and it's going to keep increasing in temperature until that liquid hits 100 degrees. At 100 degrees, that liquid is going to become a gas. And so we call 100 degrees for water its boiling point. Okay? And then if I keep adding even more heat, then that gas will increase in temperature. Okay? So this is the heating curve. Now, what we're going to be studying in this lesson is this transformation right here and this transformation right here. Okay? In the next lesson, we'll look at the energy that's involved in changing the temperature of a substance. But for today, we are specifically focusing on the heat involved in melting and the heat involved in boiling. Now, I need to make one other point. When I'm going from left to right, I'm going from a solid to a liquid or a liquid to a gas. I'm putting energy in. Solid to a liquid is called melting. Liquid to a gas is called boiling or vaporization. What if I go in the opposite direction? Well, if I'm going from right to left, I'm going from a gas to a liquid, that would be condensing. And if I'm going from a liquid to a solid, that is called freezing. All right, so first we're going to talk about the energy involved in melting and freezing. Okay, so as I had noted, to go from a solid to a liquid, you have to put heat in. Okay, you're putting heat into the system. When you're going from a liquid to a solid, heat is actually going to be released. Okay? So the values that I get when I am going from a solid to a liquid are going to be positive values because I'm putting heat in. When I go from a liquid to a solid, the heat values are going to be negative because it's being released. A fun fact, the reason why your freezers need to have fans on them is because since the process of going from a liquid to a solid releases heat, that heat has to go somewhere. And so the freezer needs to get rid of that excess heat that was released, or else it wouldn't be able to freeze the substances that it's trying to freeze, the food in your freezer. So in order to do these calculations, when I'm talking about melting and freezing, the value I'm going to use to determine the heat that's involved is called my heat of fusion. Okay? Now your heat of fusion, when you are melting, going from a solid to a liquid, will be positive. When you go from a liquid to a solid, when you freeze, it will be negative. Okay? So let's look at two examples. All right, let's look at the first example. It says, calculate the amount of heat in kilojoules absorbed when a 15.5 gram ice cube melts. So my given here is 15.5 grams. I want to get into kilojoules. So I'm going to use my heat of fusion. I'm going to put grams on bottom. And notice for heat of fusion, the units are joules per gram. So I'm going to put joules on top. And it would be awesome if that could be done, but I asked for it in kilojoules. So I'm going to do one more crisscross swish. I'm going to put joules on bottom, and I'm going to put kilojoules on top. Okay. Now, for the relationships, I know that there are 334 joules in every 1 gram. That's my heat of fusion. And I know that 1 kilojoule is 10 to the third joules. Now note that my heat of fusion here is positive, and it's positive because I am putting heat in order to melt it. Okay, so let's actually calculate this. So I'm going to take 15.5, multiply by 334, and then I'm going to divide by 1,000, and the value that I get unrounded is 5.177 kilojoules. Okay, sig figs. 15.5 has 1, 2, 3 sig figs. 334 has 1, 2, 3 sig figs. This is an exact relationship, so I'm not going to use it. So I need 3 sig figs. 1, 2, 3. So my answer is going to be 5.18, and my units are kilojoules. Okay, let's look at the next example. Calculate the amount of heat in joules involved when 4.5 grams of water freezes. Okay, so my given is 4.5 grams. Okay, it's asking for my heat in joules, so I'm going to get out of grams. And since my heat of fusion in this case is in kilojoules per mole, I've got a little situation. So your heat of fusion can either be given in joules per gram or kilojoules per mole or joules per mole. So in order to use my heat of fusion, I am first going to have to convert into moles. Okay, and I can do that in just a minute. I'm going to get out of moles now, and I can get into now kilojoules by using my heat of fusion. I'm not done though, because I asked for joules, so I have one more step, kilojoules, and then I'm going to get into joules. Okay, so grams per mole, that is going to be the molar mass of water. So the molar mass of hydrogen is 1.008. I need to multiply that by 2 because I have 2 hydrogens. And then I'm going to add to that the molar mass of oxygen, which is 15.999. And so the molar mass I get for water is 18.015 grams for every 1 mole. Now my heat of fusion here is 6.02 kilojoules for every 1 mole. Note though that I'm talking about freezing. And when I freeze, I'm going to be losing energy because the easiest way for me to remember this, I'm going in the wrong direction. I'm going this way instead of going from left to right. So I have to release energy, so my heat is going to be negative. Okay, so it's going to be negative 6.02 kilojoules for every 1 mole. And then for here, 1 kilojoule is 10 to the third joules. Okay, so now I'm going to just calculate it. I'm going to take 4.5, divide by 18.015, then I'm going to multiply by negative 6.02, and multiply by 1,000. And what I get unrounded, is negative 1,503. Keep in mind, 4.5 has 1, 2 sig figs. This has 1, 2, 3, 4, 5, 1, 2, 3. So I need a total of 2 significant figures. Okay, so this would round to negative 1,500 joules. Okay, so that is the heat that is required to melt, or the heat that is released when you freeze a substance. What about vaporization? All right, so let's now look at the process of vaporization and condensation. So remember here, if you are vaporizing, you are going from left to right. So you're going to be adding heat to do that. So the heat that you calculate is going to be positive. While when you go from a gas to a liquid, you're going backwards, the heat is going to be negative. And instead of heat of fusion now, in order to calculate the heat that's involved in vaporization or condensation, we're going to be using the term heat of vaporization. Okay, so not heat of fusion anymore, heat of vaporization. All right, so let's look at this problem. I'm told I have 33.8 grams, and it asks how much heat in kilojoules is required to vaporize that. Well, notice the heat of vaporization that I give you is in kilojoules per mole. So the first thing that I need to do is I need to get out of grams and I need to get into moles. Because once I'm in moles, now I can use my heat of vaporization, put moles on bottom, kilojoules up top in order to solve for kilojoules. And since it asks for kilojoules, I'm done. So just as a reminder, the molar mass of water is 18.015. We just did that in the previous problem for every 1 mole. Now the heat of vaporization is 40.7 kilojoules per mole. And let's check really quickly. I am vaporizing. So I am moving from left to right. So my heat of vaporization should be positive. So I'm good there. Okay. So I'm going to take 33.8. I'm going to divide by 18.015. And we're going to multiply by 40.7. Okay. So the unrounded value that I get is 76.36. Keep in mind, 33.8 has 1, 2, 3 significant figures. 1, 2, 3, 4, 5, and 1, 2, 3. So I want to have 3 sig figs in my final answer. So this would round to 76.4, and my units are kilojoules. Okay. Let's look at one more example. What is the heat change that your body experiences in kilojoules when 2.8 grams of sweat evaporates from your skin? So I'm starting with 2.8 grams as my given. Notice I'm trying to solve for my heat in kilojoules, and I'm given heat of vaporization in joules per gram. So I can get out of grams and directly into joules now, because my heat of vaporization is not in kilojoules per mole, it's in joules per gram. However, I don't want to stay in joules. I want to get into kilojoules, so I'm going to put joules on bottom, and I'm going to put kilojoules up top. Okay? So what does this mean? Well, I need to put my heat of vaporization on top, 2,257 joules for every 1 gram. And I know that 1 kilojoule is 10 to the 3rd joules. Now there's one thing I need to check. I am evaporating, which means I am going from left to right again, a liquid to a gas, which means that my heat of vaporization should be positive. If it were condensing, then this value would be negative. But because it's evaporating, this is going to be positive. So I'm going to take 2.8 and I'm going to multiply by 2,257, divide by 1,000, and I get 6.3196. Okay. 2.8 has 2 sig figs. 2,257 has 4 sig figs. So my final answer needs 2, 1, 2. 6.3 kilojoules. Now, quick side note for you to know, this evaporation process, because the evaporation of water requires heat, where it gets that heat from, it steals that heat from your body. And so that's why your body sweats to begin with. so that when the sweat evaporates from your body, it removes heat from your body and causes you to feel coolness. So when you have a positive heat, what you feel is cold. And so that is why you physiologically need to sweat.